All right, hello, greetings, and welcome. So this is part two of our notes from chapter two. So here we'll begin to talk about the quantitative modeling of the PVT phase behavior of our fluids. Okay. So in the first set of notes, we just looked at PVT phase diagrams, mainly pressure versus volume, pressure versus temperature, and then pressure versus compressibility. Z being this new property that we introduced for convenience, right, an auxiliary function, where Z is defined as PV over RT. Right, so not a fundamentally new property, but a new quantity that'll be useful for calculation purposes. Right, it's going to be a dimensionless property, which is typically bound between 0 and 1, and physically it's going to correspond to deviations of V from our ideal gas limit. Okay, and so I'll write that out on the next slide so you can see what exactly it means. So in this course, right, we're going to focus a lot more possibly than other courses on how to quantitatively model PVT phase behavior of fluids, right? So beginning in chapter 3, when we start to solve our engineering thermodynamic problems, right, when we introduce the first law, okay? As we mentioned before, if I have a single component, single phase system, I have 2 degrees of freedom, right? I need to specify 2 intensive properties, at which point everything else is fixed. Our favorite properties to work with are pressure, volume, and temperature, because they're 3 quantities that I know, understand, and can readily measure. Right, so those are going to be our favorite 3 go-to intensive properties, if you will. And again, we only need to specify 2, at which point everything else is fixed. So we talked about reading phase diagrams. Now we want to talk about quantitatively modeling, so that when we go on later and solve problems, we can quantitatively solve said problems. In a typical engineering thermodynamics course, most of the emphasis in terms of that quantitative modeling is, involves using tabulated data. Okay, and so tabulated data is great and fine, and it works well for this course because we'll primarily look at problems involving water, or maybe refrigerant 134A, right? Common refrigerant. So, data is readily available, right, in tabulated form. But what I want to look at or kind of talk about are other techniques, right? So in this course, besides tabulated properties, we will often use cubic equations of state, or we'll discuss cubic equations of state and use cubic equations of state to solve problems. Why? Because when you graduate and leave this course, right, maybe you go and you work for Whirlpool and you're trying to design novel refrigerants, right, for a given process. Novel refrigerants for which data isn't readily available or tabulated. So what I want you to do, or what I want you to, be aware of, are what tools are available to you if you ever needed to calculate or model the PVT phase behavior of fluids, and say tabulated data isn't available or isn't an option, or maybe you need some analytic equation that you can use in some, computer program that you're developing or building. Okay, at least in the world of chemical engineering. All right, most of our process simulators, commercial software which is used to model PVT phase behavior of fluids, use almost exclusively cubic equations of state, or for cases like water or more more complicated fluids, more sophisticated equations of state. Okay, so in this set of notes, we'll talk about corresponding states theory and Virial equation, and so. Again, when we have to quantitatively model, in this course we will primarily use tabulated data and cubic equations of state. So we might not necessarily leverage corresponding states theory or Virial equation, but what I'm trying to do, or I want you to do, is leave this course with some idea of what tools are out there and available to you, so that if your future career you need to model PVT phase behavior of fluids, right, you have some idea or some knowledge of where to start and where to begin to look. Okay. All right, so we're going to start with corresponding states theory. Okay, so where we left off in our last set of notes is with this compressibility diagram, so Z versus P. So Z versus P. And so again, Z isn't some fundamentally new quantity. It's a convenience function that we introduce, and it's defined as PV over RT. Significance of Z is 1, it's dimensionless, okay, and 2, okay, typically the values are bound between 0 and 1. Right? There are cases where I could be in the supercritical region and I can get values of Z greater than 1, but in general, for most processes of interest, Z is nicely bound between 0 and 1. right, with 1 corresponding to that ideal gas state. Okay, so Z is dimensionless. In general, it's bound between 0 and 1. All right, so it's, has some nice finite range compared to, say, just thinking about volume. Okay. One other point I want to just make as an aside is we said that, the equation of state for, an ideal gas, right? And this ideal gas state is P times V is equal to RT. Right? And so, PV equals RT for an ideal gas, right? So for an ideal gas, right, Z is equal to 1. Okay. So why I mention this, right, is what's common, okay, is, I should have room, right? What's common is Z is equal to, so let me rearrange this, right? So V ideal gas, right, is equal to RT over P. Okay. So what's common, right, is you can replace RT or P over RT, right, RT over P here. So this would be equal to V over V ideal gas, right? So essentially Z you could think of as being my actual molar volume relative to that of the corresponding ideal gas at the same temperature and pressure. All right, so Z is equal to V over V ideal gas. All right, so it's a measure of deviations from ideality, if you will. Where we'll use this a lot is rearranging. I could equivalently write that Z is equal to Z times V ideal gas. Okay, and where this will come in is when we, ultimately when we get to our cubic equation state and we use corresponding states theory, right? Our goal is to try and calculate Z, right? Our focus and goal is to calculate Z. Again, we like working with Z because it's dimensionless. Okay, and in general, the values are bound between 0 and 1, right? Or they're 0 to 1-ish. Okay, and so if I can calculate Z, right, then I can readily calculate V using my ideal gas equation of state. All right, V ideal gas is just RT over P. So if I put all my focus in calculating Z, V ideal gas is something that can be readily calculated. And so if I need to calculate temperature or volume, molar volume for given temperature and pressure, if I can calculate Z, I can readily calculate V ideal gas, right? And I have V. All right. So first conversation or first point that comes up is corresponding states theory. And so, corresponding states theory is one of those things that's so simple, it's, beautiful for lack of a better word. So let's try and put things into context. All right. So corresponding states theory. So the kind of the father of corresponding states theory is Kenneth Pitzer. Right. So think in the pre-computer days. Okay. So we're kind of in the pre-computer days or pre-days when computers are readily available to us. So let's think about this scenario again where I'm a design engineer for Whirlpool. Okay. So if there are 100 different refrigerants that I could possibly want to evaluate for a given process. And I want to solve problems, right? Well, what am I going to do? Am I going to perform, extensive, experiments for all 100 of those refrigerants to, be able to tabulate PVT properties of them, right? So that I can go on and solve problems, right? That seems incredibly inefficient for design schemes. So kind of the goal of corresponding states theory is, can I measure PVT properties once, right, for a fluid, call it a reference fluid, and then rescale that to be able to predict properties for any fluid of interest, right? So kind of our goal here is achieving data collapse. So rather than measuring PVT phase behavior for 100 fluids, could I just measure it really well for one fluid, and then with that data that I've measured really well for one fluid, can I predict data for others? And so kind of where the aha moment comes in is here I have my compressibility phase diagram. And so what Pitzer realized is that if I take my PV phase diagram, right, and I look at PV phase diagrams for a lot of fluids, they look really similar. And so what he discovered is that if he plots in reduced coordinates, by reduced coordinates, so I have Z, and so instead of using P for my x-axis, I'm going to use reduced pressure, so pressure divided by critical. And for my isotherms, right, I'm going to plot reduced isotherms, so temperature divided by critical temperature. So when I plot in these reduced coordinates, at least for simple fluids, I achieve data collapse. right? So it's plotted here, right, are essentially relatively simple fluids. So I have argon, nitrogen, methane, carbon dioxide, ammonia, and heptane. Okay, and so they're spread in the data, right? Because this isn't a perfect model, right? But it does a pretty good job, right? So kind of, it was kind of this, big aha moment of wow, right? I can achieve data collapse when I plot and reduce coordinates. So kind of, you need to think of or appreciate the significance of this. So again, I can model one fluid really, really well, right? I could spend all this time measuring really accurate PVT phase behavior for one fluid. And then if for another fluid, I just measure its critical temperature and pressure, that's sufficient to be able to take my reference data that I measured really well and rescale it to obtain the PVT phase behavior for that fluid. Right? It's pretty remarkable and cool. Okay, and so this is kind of an idea. Okay, and it works okay for what we'd call these simple molecules. Okay, but there's definitely deviation. Right, so you can see the spread, right? The agreement isn't perfect, okay? But, the first, key takeaway here is the idea of corresponding states theory is that when I plotted and reduced coordinates, I can get data collapse. This is huge and significant for design applications in terms of trying to reduce or minimize the amount of data that would otherwise need to collect or tabulate to be able to, go through these design schemes of comparing, say, different refrigerants, different fluids. Okay, but it's not perfect. And so, where things, evolve from there is we call this two-parameter corresponding states theory, right? I plot with respect to reduced temperature and reduced pressure, right? So I need TC and PC to plot and reduce coordinates for this to work. Okay, and it works well for what Pitzer called these, simple spherical molecules. Okay, but if I were to throw something like water on there, right, the deviation is going to be even greater. And so what's even more amazing, okay, is, he then introduced a third property called the eccentric factor. And, so my recollection of the story is okay, we've got this two-parameter corresponding states theory that works really well for these, simple molecules. But if I look at things like water, right, they deviate significantly from two-parameter corresponding states theory. So, again, thinking in terms of, World War II era. So before, computers were, as powerful as they are or as common as they are, Pitzer then proceeded to look at a bunch of P versus T phase diagrams, right? And so, you could take your P versus T phase diagrams, you could likewise plot those in reduced coordinates. So you could plot your reduced pressure versus your reduced temperature. And so what he found is that for these simple fluids, right, they all seem to intersect, all right, at a common point. Okay. And then for these other molecules, all right, they didn't intersect at this common point. And so this, essentially he attempted to measure this deviation, all right, and how he measured this deviation is using this additional parameter omega, my eccentric factor. All right, and so the eccentric factor is by definition -1 minus log base 10 of the reduced saturation pressure at a reduced temperature of 0.7. Okay, so again, the basic idea, right, so from my memory, is that, Pitzer was looking at now P versus T phase diagrams plotted in reduced coordinates, and what he found is for these simple fluids, they all intersected at this common point. Okay, for, these non-spherical molecules, right, so water, right, or other more complicated molecules, they didn't intersect at this common point, right? So what he did is he took that common point, right, tried to measure a deviation from that common, reference state, if you will. Okay, and that's a eccentric factor. So he introduces a third parameter, and then he extends the method so that he has Z naught, which is my compressibility that you would get from two-parameter corresponding states theory. So if I'm a simple fluid, my eccentric factor is just 0. Right, is how we set this equation up. And then he has a correctional term. So Z now is going to be listed as Z naught, which is just a function of reduced temperature and pressure. Okay, two-parameter corresponding states theory. Plus, I have a correctional term, which is my eccentric factor, which is my deviation from this, spherical, simple spherical limit, times Z1, right, which is likewise just a function of reduced temperature and pressure. Okay, so Idea here being corresponding state theory is great. Pitzer realized that if he plots reduced coordinates, he can get data collapse. That only works well for simple spherical molecules. So what he does is he introduces a third parameter to try and improve, the ability to make quantitative predictions. The third parameter he introduces is this eccentric factor, which is related to the reduced saturation pressure at a reduced temperature of 0.7. And so with that, he's able to achieve improved predictions for Z using this equation, Z naught plus omega Z1. So for simple molecules, omega is 0. For non-simple molecules, omega is non-zero. And so this term will be non-zero. Z1, he found, is also just a function of temperature and pressure. Okay, so it extends the range of applicability. It's not great, but extends the range of applicability. And again, it's just so simple. It's beautiful, right? Again, think about the time in which this was done. Okay. Now I will mention it that we will leverage three-parameter corresponding states theory when we talk about cubic equations of state. But this is kind of the origin of where all that comes from. Okay. All right, so we said Z naught and Z1. Okay, those are functions of my reduced temperature and pressure. Right. All right. Okay. So just essentially said all that. So Z naught and Z1 are functions of reduced temperature and pressure. Where do we get those? Right. So in our book, Matsukat's book, he provides graphs for Z naught and Z1. So they're graphs where if you know TR and PR, right, you can read off Z naught and Z1. Okay, and so graphs are great, but they can be kind of hard for making good quantitative quantitative calculations. So there's another appendix online on Canvas scanned up from another textbook which contains these Lee-Kessler tables. And so Lee and Kessler essentially just try to tabulate, if you will, the generalized graphs which are provided in the book. All right, and so again, the idea being if I know my reduced pressure and I know, say, my reduced temperature, then I could look up the value of Z naught and then likewise Z1. Okay, so they're just functions of reduced temperature and pressure. I'll often use these Lee-Kessler tables, and that's why I scanned up appendix from that second book to make it easier to perform quantitative calculations. Okay, again, corresponding states theory is just so simple and beautiful. All right. The other equation that we'll mention is the Virial equation. So the Virial equation, its significance is that it's essentially our only theoretically based or theoretically correct equation of state, if you will. Okay. So you can cook up the Virial equation using first principles from statistical mechanics. And so one way to look at it is here Z, my compressibility, Z is PV over RT. So here I'm just writing Z as a power series expansion with respect to P. Okay, so B, C, and D would correspond to, we'll call them Virial coefficients, right, which are going to be a function of T. All right, so Z is just a power series expansion about P. So in the limit that P goes to 0, right, I create achieve the correct limiting behavior that Z is equal to 1. The other way that it's typically written is rather than a power series expansion with respect to P, it's written as a power series expansion. Here I'm writing as a power series expansion with respect to V, my molar volume. Okay, but remember that V is just equal to 1 over density. Okay, so 1 over V, right, is really rho. So here I'm writing as a power series expansion with respect to inverse molar volume, but it's really a power series expansion with respect to density. Okay, so those are the two common forms. Okay, so again, B, C, and D, right? We would call those Virial coefficients. Okay, the two forms, whether you expand with respect to P and V, of course, they're related to each other. Now, I said this is our, physically based, our only theoretically based or physically based equation of state, which you can derive using statistical mechanics. And so, the significance of our parameters is, Z, again, is just this ideal gas limiting value, right, our 0th order term. Okay, Then B, right, we call our second virial coefficient, right? It's the second term in our series. And this corresponds to two-body interactions. So we won't delve too much into it, but if I had a mixture of water, right, that's a corresponding to that, the total interaction energy of my system would be the sum of how these pairwise interactions, water interacts with one other water molecule. So if I could tag them all, if I had molecules 1 through 100, right, one would interact with 2 all the way up through molecule 100. Okay, then likewise, molecule 2 would interact with molecules, I guess not to double count, 3 all the way up to 100, and so on and so forth. The total interaction energy would be the sum of all those, pairwise interactions, two-body interactions. All right, so B, it counts for those two-body interactions. C would account for three-body interactions. D, four-body, and so on and so forth. All right, so they're fundamental physical-based quantities. Okay. The issue with our Virial equation is typically, you don't know all these terms. So the value of our Virial coefficients typically aren't known, and so in the book, right, in the text, they'll talk about the truncated Virial equation. And when they talk about the truncated Virial equation, they're typically just truncating after the second term, and so they're just looking at equation of state of this form, truncated Virial. Motivation being is typically we don't know Virial coefficients, or they're not common beyond that second Virial term. Okay, so again, it's trying to give you an idea of what's out there for future purposes and applications. Now I will mention that I know in NIST, so they use helium a lot to calibrate a lot of their instruments. So helium is a common standard fluid, and so at NIST, for helium, they actually have Virial parameters for helium out to, many, many terms, right? And so reason being, or why are they working with, Virial equation? Well, helium is a quantum fluid. But, it's a standard, so they're going to use their, most theoretically based correct equation of state to try and model the phase behavior of helium. So the book will talk about truncated Virial coefficient, which is just truncated after that first term. And again, that's just typically that's all that's available to us. Okay, and so because of this, the range of applicability, if I'm just truncating after one term, is going to be extremely limited. All right, essentially this is just a first order correction to my ideal gas equation of state. Okay, so the two forms of the Virial equation are related. You could work out that relationship. All right. Again, if I were to truncate after one term, right, that's just then corresponds to first order correction about my ideal gas state. So I can think about a Maclaurin series expansion about the limit that P goes to 0, my ideal gas state. All right, that first term is just that first order correctional point. And so if I'm dealing with truncated Virial equation, its range of applicability is extremely limited. Right, so you would only use this when your system is close to that ideal gas limit. Okay. The last point that I'll just make is there are corresponding states theories available as well for Virial coefficients. I've seen corresponding states available for second and third Virial coefficients. So here's an example of Pitzer's equation for that second Virial coefficient. So again, Virial equation in practice isn't used all that much. Why? Because we're limited in available parameters. So typically only second Virial coefficients are available, which don't allow us to extrapolate very far beyond that ideal gas limit. Okay. Fundamentally, though, it is our only theoretically based equation of state, so it's fundamentally important. Okay. I will mention that at least in physical chemistry world, second Virial coefficients are often used or measured for things as complicated as proteins in solution, because they can be related to radial distribution functions that can be measured using X-ray diffraction, and are used as a way to try and quantify the intermolecular interactions in your system, right? Those pairwise interactions. Okay, but there's corresponding states theory. There's Virial. In the next set of notes, we'll talk about cubic equations of state, which again will be our main workhorse along with tabulated properties in this course. Okay, I want you to read the chapter. I want you to think about all this. not because we're going to solve problems using Virial equation in this course or necessarily corresponding states, but when you graduate and you go on and maybe you're a design engineer and you don't have tabulated values for a problem, I want you to be aware of what tools are available to you to solve real problems, right? And at least in chemical engineering, cubic equations of state are indispensable for the design of chemical plants. Okay, so I look forward to seeing you in the next set of notes. Let me know if you have any questions.